It's a good question, and the very short answer is we don't know. That's a surprising thing to say, though, because what we do know is that 13.8 billion years ago, the universe was very, very different indeed to the universe that we see today. So today we see this universe full of stars and planets and galaxies, complex structures. What we know is that as you wind time backwards and you go back 13.8 billion years, there were no stars, no planets, no galaxies. The universe was very hot and very dense. And we call that moment, if you like, in the history of the universe, the Big Bang. And it's always been synonymous with the origin of the universe, I think, in most people's minds. And indeed, that's the way that the key point. So we used to think that, if I rewind a bit, the framework that we use is Einstein's theory of general relativity. It's published in 1915. That theory strongly suggests that the universe is not stable in the sense that it should be expanding or contracting. And Einstein actually resisted that. So the theory is really strongly suggesting that space itself should be stretching or shrinking depending on how much stuff is in it. And most people at the time, I think, Einstein included, thought that the universe should be eternal because it just feels better. You know, you don't have to deal with thorny issues about a moment of creation or the origin or what caused the universe to come into existence, or whatever you want to say. Right. Well, many people thought, well, it's a good question, isn't it? So we'll get to that. So I think most people kind of thought it was eternal, although obviously then you have various religions with creation myths and so on. But Einstein's theory strongly suggests that it should be changing. Then the observations in the 1920s by people like Edwin Hubble showed that the universe is indeed stretching, right? The fabric of the universe itself is stretching, the universe is expanding. That caused people like Georges Lemaitre, who was one of the founding founders of cosmology. He was a very interesting man, actually, a Belgian priest, as well as a physicist and a mathematician. Cool. Caused him to say that it seems the universe had a day without a yesterday. Because if you just imagine, if the universe is expanding today, then that means yesterday everything was closer together and you can rewind time until everything's on top of each other. And we call that the Big Bang. So that's kind of what you learn in school, right? And that's the basics of picture we have of cosmology. But whether or not that time when the universe was hot and dense is indeed a day without a yesterday, if that's a first moment, or whether the universe existed in some other form before that, and indeed whether that other form goes into the infinite past, is just not known. I should say we strongly suspect the universe was in existence before it got hot and dense. And that's a theory called inflation, which is essentially the idea that the universe was empty and cold pretty much before the hot Big Bang, and expanding very rapidly indeed. And that expansion drew to a close. All the energy driving that expansion was kind of dumped into space, which heated it up and made the particles out of which we're made. But when that began, or if that began, honestly, we don't know.
Yeah, I want to talk about kind of a small goal. I want to talk about the universe, but particularly the two great pillars of our understanding of the universe that we've built over the last century. And we're still building absolutely now. Two of those pillars that I hope you're going to contribute to building in the future. The two pillars, two things that maybe you don't learn about at school, but you'll certainly learn about at university. One pillar is called relativity, which is Einstein's great contribution to science. And the other one is something called quantum mechanics, which is a fascinating theory. It seems very strange. You may have heard of things like Schrodinger's cat. Things can be in two places at once. But actually, quantum mechanics is our theory of everything that happens in the universe other than gravity. And today, the place where we explore that in detail is the Large Hadron Collider at CERN in Geneva, the place that I work when I'm not messing around on television. So I want to give you some idea of what we're doing now at the Large Hadron Collider and what we hope to discover within the next year or two. So absolutely current cutting-edge research. But the first thing I think to say about the ambition, because I said we want to understand the universe and our two great theories of it, is to look at the sheer size of the problem. And that's one of the things that I think captured my imagination first, when I first began to get into science, when I was 5, 6, 7 years old. It was the sheer ambition of it. Because This is a picture of the universe. This is actually a picture of the night sky. If any of you are interested in astronomy, that thing up there is the constellation of Orion that you can always see in the winter sky. But I want to I want you to focus on a piece of sky that's somewhere around here. I'm going to zoom in on it now. It's a piece of sky that you would cover if you took a 5p piece and held it about 25 metres away. So imagine taking a 5p piece and putting it 25 metres away over a tiny piece of sky. Well, a few years ago now, the Hubble Space Telescope, which is in orbit around the Earth, turned its gaze to that tiny piece of sky, the 5p piece bit of sky, and took a picture. It opened its camera shutter for thousands and thousands and thousands of seconds and just gathered the light from that piece of sky. It was deliberately chosen because it's a dull, uninteresting piece of sky. Actually, from the surface of the Earth, you would see virtually nothing in it at all. But this is the picture that Hubble took. And you see that it's anything but empty. It's called the Hubble Deep Field image. It's one of the most important and fascinating images in the recent history of astronomy. It's not empty. It's got lots of structure, lots of points of light in. There are actually over 10,000 points of light or blobs in that image. And virtually every one of them, over 10,000 of them, are actually galaxies, distant galaxies. So they're not stars, they're galaxies. Now those galaxies on average have, 100,000 million stars like our sun in them, at least. So 100,000 million stars in each one of those 10,000 blobs. The most distant object in that image, and I'm going to talk a bit about how we know these things in a moment, but the most distant object is 13.2 thousand million light years away. It was actually discovered in this image only a few months ago. Now, light travels at 300,000 kilometers per second, 186,000 miles a second. And at that speed, it's taken over 13 billion years to travel from the most distant object in that image to Earth, to the Hubble Space Telescope. Now, when you think that the Earth is only just under 5 billion years old, it means that most of the light from most of the galaxies in that image began its journey to Earth before there was an Earth. And for some of the most distant galaxies there, they were over halfway here when the solar system was just a cloud of gas and dust. It hadn't yet coalesced into the sun and the planets and moons of the solar system. So imagine what that looks like. That's a tiny, remember, 5p piece of sky 25 meters away. Imagine what that looks like when you extend it over the entire sky. Well, this is a beautiful map of the observable universe. Every dot on that map is a galaxy, with 100 billion stars like our sun in it, at least. You see that the structure in there, they're not randomly distributed. It's very interesting. I'm going to show right at the end of the talk that we think we're beginning to understand where that structure came from. Just to get some sense of scale, that little line up there, you might not even be able to see it at the back, but that's the 1 billion light year line. So light takes 1 billion years to travel from one end of that line to the other. This is the observable universe. And I'm going to show you, there's a ridiculous number that I have to show you. It's better to show it than say it. This is the number of stars that we think are in the we know from observation are in the observable universe at the moment. 30,000 million stars. Just like our sun, some bigger, some smaller. 350 billion large galaxies, 7,000 billion smaller dwarf galaxies. That's the observable bit of the universe. We have pretty strong evidence now the universe is significantly bigger than that, but we can just see this blob surrounding us, the blob from which light has had chance to travel during the history of the universe. So the universe is big, is what I wanted to say to you. I don't know if you know a comedian called Woody Allen. He once said that the universe is probably infinite, which is a bad thing if you're one of those people who can't remember where they put things. But it's enormous. So how can you... Oh, I don't want to start that yet. There we are. So how can we possibly begin to think about explaining that? How do we know, first of all? How do we know it's so big? How did we find that out from this planet that we're standing on now? And how could we begin to make theories, guesses, I suppose, if you like, about where that came from, how it began, how fast light travels, all those facts that I've said to you, or all those numbers that I've given out that are our best estimate of how the universe works. It is, of course, science. And I wanted to just play you a little video of, for me, what the best definition of science, or the scientific method that I've heard. It comes from a very famous physicist called Richard Feynman, who won a Nobel Prize for building one of the first quantum theories of electricity and magnetism. It's called quantum electrodynamics. This is back in the 1940s and 50s. It's our best theory today of how light interacts with matter. How can we possibly compare ideas about the origin and evolution of the universe with nature? Well, if you think about it, there's only one way to look into the wider universe from Earth, certainly the universe beyond our solar system, and that's to gather the light from distant stars and planets. And there is an immense amount of information contained within that light. This is our sun. It's a tremendous, I think, video of the sun. This is not a computer graphic, it's a real movie of the sun taken by an orbiting spacecraft that just observes the sun every day. And you see that it's a dynamic and violent place. You could fit 1 million Earths inside that ball of glowing plasma, by the way, 1 million planet Earths. It burns 600 million tons of hydrogen fuel every second into helium. So it's a powerful, gigantic object. Many years ago now, stretching back to Newton and even before, we looked at the light from the sun, and after Newton we found a way of analysing it by splitting it up into its component colours. So with a prism, essentially making a rainbow of the light from the sun, just as nature makes a rainbow of sunlight using water droplets. And this is a picture, a modern day picture of that rainbow. Now, rainbows, of course, lots of different colours from blue all the way to red, but when you look at the light from the sun in a laboratory and you're very careful and you put it through a very precise prism, then you see that it's not just an array of colours, it has dark lines in it. All these black lines crisscrossing the rainbow. What those lines are the signatures, the thumbprints, if you want, of the chemical elements themselves. See, what happens is you'll know that an element is a nucleus with electrons going around it. And each element has a different nucleus and a different arrangement of electrons. What happens with the light from stars is that the light shines through elements in the star's atmosphere, so elements like hydrogen and oxygen and helium. And because those elements have different structures of electrons around their nucleus, they absorb different colours of light, very specific colours that correspond to moving the electrons around in very specific ways. So, for example, these two lines here are very famous. They're called the sodium lines. Sodium absorbs light in the yellow part of the spectrum. If you heat sodium up, it emits light in the yellow part of the spectrum. Why? Because of the way its electrons are arranged around the atom. So what you're seeing here is the signature, the fingerprints of elements in the sun. That's interesting in itself because you can immediately read off what the sun's made of, because you can do an experiment on Earth, see which colours the elements absorb or emit, and you can look in the starlight. You can see what the stars are made of. But also, and this is the point for looking at the wider universe, something very interesting happens when you look at these spectrum, these black lines in the rainbows of the most distant stars and galaxies. So here's a distant galaxy. You can look at the light from that galaxy. What you find, of course, is that the spectrum is the same. The black lines are all the same because chemical elements are the same across the universe, except that in all distant galaxies, the lines are shifted. They're moved. They're not in exactly the same place. Now, one explanation for that, of course, could be that the elements are somehow different in different parts of the universe. But it's interesting, isn't it, that they're all shifted in the same way. And actually, there turns out to be a pattern to this shift. So what's the explanation? Well, the explanation for the shift is very simple. The universe is expanding. So if you look at a very distant galaxy, then you find all the distant galaxies are rushing away from us. Think about what that does to the light. What happens to the light is the light begins its journey from the distant galaxy. Light is a wave. You just imagine a wave on its journey through space. The space is stretching because the universe is expanding as the light journeys from the distant galaxies to us. What does that do? Well, it stretches the light. So the wavelength of the light is stretched. The wavelength is the colour. red light has got a bigger wavelength than blue light. So as the light, let's say it comes from a star, it's a hydrogen, let's say, emits a line up here, and that journeys across the universe to us, it gets, actually, let's start in the blue. So let's say there's an element down here that emits light in blue. It journeys across the universe, it stretches, it moves towards the red bit of the spectrum because it gets stretched. And so you see the whole fingerprint of the atoms moved from the blue bit of the spectrum to the red as the light gets stretched, as space stretches. That's what we observe. So that's a very direct measurement that tells us that the universe is expanding. That's one piece of the puzzle.
Perfect question.
Thank you.
Because it seems impossible, doesn't it? It seems, how can you know?
Yeah.
How can you measure the distance to a star, for example?
Like, how can you?
How do you know?
Did you just
It was
decide?
a tremendous effort. If you go back to the 17th century, 16th century, 18th century, the LHC, the Large Hadron Collider, or the Apollo program of the time,
Right.
was to try to measure the distance initially from the Earth to the Sun, which is called 1 astronomical unit. And that was done in a very subtle and clever way by watching something called the transit of Venus, which is when the Venus floats across the face of the Sun. And by watching it from different positions on the Earth, you can do some geometry, and they were very smart. And they figured out they could use this to find the distance from the Earth to the Sun.
Amazing.
Once you have that, you use parallax, believe it or not, to get the distance to the nearest stars.
Right.
Because
What's parallax?
So parallax is, with your eyes. If you close one eye and then close the other eye, and something moves, right? Yeah. So you do that, and it moves.
That makes sense.
It's because of the distance between your eyes, and so you close one, you close the other, and the angles change a bit, and you can see how far something is away, and that's how you perceive depth to some extent.
Yeah.
If you know the distance from the Earth to the Sun, then you can look at the position of a star in the sky in, let's say, January, and then look at it in July, and you've gone halfway around the Sun. So your eyes, in that case, are twice the distance from the Earth to the Sun, right? 180 million miles or something like that. And you see the star shift a bit,
Yes.
right? Because it's just the same as doing that, right? From
No
January
way.
to June. And that's how you do the distance to the nearest stars. And then from then, what happens is you try to find some relationship between the brightness of a star and something else that it does. And there are things called variable stars, which vary. So they go light and dark and light and dark. And they vary in a way that's proportional to how bright they actually are, which is a really thing they call Cepheid variables. And so if you know how bright something is, actually, and you know how bright it looks, then you can guess how, or calculate how far away it is, right? Because the further away it is, the dimmer it is, because you know how bright it is. So that's another way of doing it. Then we have things called Type 1a supernova explosions, which are very bright, and we know how bright they actually are, and we can see them in distant galaxies. And that allows us to tell how far away the galaxies are. Then finally, which goes to the end of your question,
Right.
you find that if you look at very distant galaxies, then the light from them is stretched, means it goes redder, because longer wavelength light is redder. It's called redshift. And you find that the further away the galaxy is, the more stretched the light is. So it's a direct measurement you can make. And that tells you how fast the universe is expanding. Because what's happened is the light has been traveling across space for, 50 million years or 100 million years, or billion years, whatever. Let's say you can see them out to 10 billion years or something like that.
That's crazy.
Right.
And it means that the light has been traveling for 10 billion years across the universe. And if it's stretched by, let's say, a factor of 3, then it tells you the universe is stretched by a factor of 3 during that time. So that allows you to measure the expansion rate of the universe. And if you know how fast it's expanding at all these different times, then you can wind it back using Einstein's theory, actually, to go, when was everything on top of each other? So it's a whole thing that began back in the 1600s with these and 1700s with these missions around the world on sailing ships.
Amazing.
There's to measure the transit of Venus, and then you get the distance, and then you get another distance, another distance. It's called the distance ladder. So it's a story that spans centuries. This idea that people just wanted to measure distances, the distance to the stars. So there are lots of multiverses, actually, in physics. One of them is called the inflationary multiverse, which is we have a theory of essentially what happened before the Big Bang. Right? You have to be careful with the language. So if you define the Big Bang really carefully as the time when the universe was very hot and very dense, and as I said, you can't argue with that because we can see it, because we can look out into the sky. Our best theory of how the universe got into that state is that there was a time before that, and it's called inflation. So the idea is the universe was there, in a sense, cold and empty and expanding extremely fast. And that expansion slowed down and stopped. And the energy that was driving that expansion got dumped into space, heated it up, and made all the particles out of which we're made. And that's what we call the Big Bang. So that's textbook. It's a textbook theory called inflation. It made predictions, some of which have been tested. Some incredible predictions, actually, about the way that galaxies are distributed across the sky, because they're not just random. If you look at the galaxies, they're in sort of flows and rivers of galaxies that cross the sky in a pattern called the cosmic web. And inflation predicted that before it was seen, actually. So it's an astonishing idea. And that theory has a kind of an extension called eternal inflation, which is that the inflation essentially goes on forever. And it just stops in little patches. So you imagine the fabric of the universe, space-time, stretch, and then it slows down and stops in little patches, and each one of those patches is basically a Big Bang and a universe, of which ours is one. So you end up with this sort of picture of an infinite fractal universe of basically an infinite number of Big Bangs, and that's called the inflationary multiverse. And it answers some neat questions, because if you say, why is our universe the way that it is? Why are the laws of nature such that life can exist, for example? Well, the answer might be that all possible combinations of all the laws of nature exist in the inflationary multiverse. So then it's not surprising there are universes that permits things like us to exist, because every possible universe exists in the inflationary multiverse. And that's a well-supported theory. It's a theory, so this is not the same as saying there was a Big Bang, which we know. This is kind of, what's a theory? It's a guess, basically. But it is a theory that in its simplest form has made predictions that have subsequently been verified. And we could go on then. There's the so-called many worlds interpretation of quantum mechanics, which is more kind of Marvel film kind of multiverse, where, so quantum mechanics it's a probabilistic theory. So imagine a quantum coin, I call it. And the quantum coin it doesn't have to be heads or tails, it can be heads and tails. Well, so the way that the Earth will end, ultimately is as a cinder, right? It's because what's going to happen is that the sun, starting in a few billion years' time, actually, but it's going to start growing. It'll grow as it gets older, and it'll swell up. It probably won't engulf the Earth, but it'll get close. The Earth will probably drift out because the sun will lose some mass. So but it'll toast it, basically. So the Earth will end up toasted as a cinder, probably still orbiting the remains of the sun, which will be what's called a white dwarf star, which is just something that basically fades away. So that's what's going to happen in about 5 billion years. I'm laughing because it's, well, that's what's going to happen. So that's how our world ends, as a crisp, basically a cinder. If you mean by the end of the world, you mean the end of civilization, then long before that, we'll have had to escape, because it will become, the conditions on the planet will not support complex life like us. It'll be too hot. But the possibility is that we discussed we could destroy ourselves, which is, it would be, given that it's quite possible that there is nowhere else in a galaxy, then, as we said before, that would be a really silly thing to do. So I think it's more likely, we might not have to wait for the sun to do it, because we might do it through our own stupidity.
You see, there are certain types of objects, certain types of phenomena that occur out there in the universe that we know the brightness of very accurately. Now, imagine how useful that is. If you know how bright a light is, and you put it somewhere a long way away, and then look and see how bright it looks to you, then you can work out how far away it is. It's very simple. Obviously, it gets dimmer and dimmer the further away it is from you. Now, this is a picture of one of the types of object that we know the brightness of very accurately, and it's actually this one here. Now, this is a beautiful picture. This is the galaxy. So this is an island, as I said, of 100,000 million, perhaps 200,000 million stars like our sun. There are perhaps 1 billion stars in the center of this galaxy, shining brightly. This looks like a star that must be closer to us than that galaxy because it's so bright. It actually isn't. It's actually something called a supernova explosion. This is a star in the galaxy. It's on the edge of the galaxy. It's the same distance away as the billion or so suns in the center and the 100 billion or so stars in the disk. Same distance away, but it's going as brightly as 1 billion suns. How could that be? One star glowing as brightly as 1 billion? Well, it's something called a supernova explosion. It's the death of a massive star, but it's actually a very interesting one. What we think that is, it's called a type 1a supernova. It's something called a white dwarf. So that's the ultimate fate of the sun. It's a star that's burnt out all its fuel and is just sitting there in space, gradually fading away. But it's a white dwarf that had a companion star orbiting around it. Now, the white dwarf, the dying star, sucks matter off the companion star until it gets too big to support itself, too massive to support itself, and then it collapses and it explodes. And we know that process very well. It was a process that was predicted, actually, from quantum mechanics, from our theory of atoms and molecules back in the 1930s. So it's a very specific process, and we can calculate precisely how brightly that explosion should be because we understand the mechanism beautifully. So we know how bright that is. We know how bright it looks because we've taken a picture of it, so we can work out how far it is away. And this is the second bit of evidence you need. So we've got two things now. We've got that you look out into the sky and you see that things are speeding away from us because you can measure the shift in the light. And we know exactly how far those things are because we can look for things like this, supernova explosions in the distant galaxies. Now, these are rare. You get on average about 1 supernova per century per galaxy. So very rare, but there are a lot of galaxies. And this is a beautiful picture, I think, again from the Hubble Space Telescope, which is a picture of galaxies along the bottom as they usually look, and along the top as they looked on a particular day or a particular week when we were looking at them when there was a supernova explosion. So you see here, there's the galaxy as it usually looks, there's a supernova explosion. Galaxy, supernova, galaxy, supernova. Supernova in hundreds of galaxies have been measured, and we've made a map of the universe. We've got the distant galaxies, we know how far away they are, we know how fast they're receding. What we find is something called the Hubble law, and it's basically very simple. It says that the further a galaxy is away, the faster it's flying away from us. Now, how are we to interpret that? I mean, you might naively say, well, does that mean we're somehow at the center of the universe and everything's flying away? Well, no, actually. If you think a little bit more, if you think, for example, about baking bread, if you get a lump of dough and put raisins in it and stick it in the oven, then the bread expands. So all the raisins move away from every other raisin. If you were sat on one raisin, what you would see is the Hubble law, exactly the Hubble law. You'd see the ones close to you moving away more slowly, the ones further away moving away quicker, because the bread is all stretching. All of space is stretching at a constant rate. So you get this fascinating law, which is exactly what we observe. It does actually turn out remarkably, the Hubble constant can be written like this, 42 miles per second per 3 million light years. What does that mean? It means that for every 3 million light years you go away from the Earth, then things, if you go 3 million light years from Earth, so let's just step 3 million light years away, then on average things will be moving away at 42 miles a second. It's pretty slow, actually. If you go 6 million light years, things will be moving away at 84 miles a second, and so on. So every 3 million light year step you take, you add another 42 miles per second to the recession velocity of things. Now, there's something else, which is actually an exercise you can do if you like doing a bit of maths, and maths, I think, is fun eventually. Not always, but eventually. What you look here is you see this is the distance, right, in miles. I've written in miles so that I could have 42 there, but you could turn it to kilometres easily enough. So that's a distance. That's a distance, 3 million light years. You could write that down in miles or kilometres as well. It's an easy thing to do. You just type it into your calculator, you can do it. Kilometres, kilometres cancel out. So the Hubble constant is actually, the units of the Hubble constant are 1 over seconds, right? Because these go away, distance goes away with distance, you've got 1 over seconds. So that implies that maybe you could flip it over, right? You could say, well, so what if that's 1 over seconds and I flip it over, do 1 over the Hubble constant, I get a time. What's that time? Well, that time turns out to be the age of the universe. So you can do it really simply. Convert light years to miles, or convert miles to kilometres and light years to kilometres, cancel them out, flip it over, you get a number. And the number is, well, with the most accurate modelling we've got today, that one, you'll find that you get something that's of order 14 billion years if you do that sum. Very simple sum to do. Actually, this is the most accurate, I think it's remarkable, the most accurate determination of the age of the universe we have at the moment, 13.73 plus or minus 0.12 billion years. That's a remarkable measurement, isn't it? That's the age of our universe measured by simply looking at the light from the distant galaxies.